A review of criticality accidents. The introduction. Link in the description below. Criticality accidents and the characteristics of prompt power excursions are discussed. 60 accidental power excursions are reviewed. Sufficient detail is provided to enable the reader to understand the physical situation, the chemistry and material flow, and when available, the administrative setting leading up to the time of the accident. Information on the power history, energy release, consequences, and causes are also included when available. For those accidents that occurred in process plants, 2 new sections have been included in this revision. The first is an analysis and summary of the physical and neutronic features of the chain reacting system. The second is a compilation of observations and lessons learned. Excursions associated with large power reactors are not included in this report. This revision of a review of criticality accidents represents a significant expansion of the prior edition with the inclusion of 1 Japanese and 19 Russian accidents. In the first 2 parts of this report, 60 criticality accidents are described. These are divided into 2 categories: those that occurred in process facilities, 22, and thus were unexpected, and those that occurred during critical experiments or operations with research reactors, 38. These 2 categories are based on the following considerations. Process facilities carrying out operations with fissile material avoid criticality accidents through physical and administrative controls. These controls are intended to prevent critical or near-critical configurations from ever occurring in the facility. Operating personnel are usually not technical experts in criticality physics. Under normal working conditions, however, operating personnel can be close to, arm's length from, potentially critical configurations. In contrast, reactor and critical experiment research facilities purposefully plan and achieve near critical and critical configurations. These operating personnel are usually experts in criticality physics. Although they carry out hands-on operations with fissile material under restrictions similar to those found in process facilities, the planned near-critical and critical configurations are performed under shielded or remote conditions. In most cases, the descriptions of the Russian accidents are somewhat lengthier than those that occurred in other countries. This is attributable to the lack of generally available references for the Russian accidents. In other words, the descriptive information in this report is all that is effectively available for these accidents. It has been gleaned from both the original Russian notes and discussions with those who had personal knowledge of the accidents. With the exception of addition of 6 Russian critical experiment accidents, Part 2 of this report is basically unchanged from that of the second edition. Although this edition is planned to be available in both English and Russian language versions, decisions have been made concerning units and terminology, particularly in the English language version. We have attempted to conform to common international usage. However, units as originally reported are sometimes retained for historical accuracy. Also, we have chosen generally understood terminology and avoided terms that might be facility or industry specific. For example, the word vessel is used to describe most solution holding containers. Thus, filter vessel is used instead of filter boat, a common U.S. chemical industry term. In Part 3, a brief discussion of analytical methods and quenching mechanisms for power excursions is reproduced from the first revision. 2 appendices are also new to this revision. Appendix A is a reproduction of LA 11627 MS, Glossary of Nuclear Criticality Terms, supplemented with 1 additional definition to assist the reader. In Appendix B, diagrams of each of the 22 process vessels in which the accidents took place are shown along with tabular summaries of the system parameters, mass, volume, etc. The emphasis of this revision has been threefold. First, it was to include the 1 Japanese and 19 Russian accidents. 14 of these took place in process facilities and 6 happened during critical experiments and research reactor operations. A second focus of this effort has been to thoroughly review the 8 process facility accidents described in the prior revision of this document and their supporting references. This led to some technical corrections and modest expansions of the process descriptions for the benefit of the expanded audience that this report has attracted over the years. Third, 2 analyses of the 22 process accidents are included. These are 1. Physical and neutronic characteristics with an emphasis on understanding systematic features, and 2. Observations and lessons learned from these accidents.